Hello and welcome to Lecture 3 of the Operations Management course. Today we will continue the topic that we have started in the previous lecture, which is about demand forecasting. So far, in the previous lecture, we talked about what is forecasting and what are the different forecast horizons. We talked about the difference between objective and subjective forecasting methods. We also illustrated the causal models, which are the models that belong to the objective classification of the forecasting techniques. And we demonstrated how to use linear regression analysis to analyze the correlation between the demand and any other factor that we wish to consider. And also we talked about some time series models such as the moving average, exponential smoothing, and double exponential smoothing, or what's called the Haltz model. Today we are going to talk about another time series forecasting models that are specifically designed to deal with demand that exhibits seasonality. We will talk about first methods for seasonal stationary series, in which the demand is almost level with some seasonality effect. And then we will talk about seasonal factors for moving averages. That's when we use techniques similar to the moving average to forecast demand, and we wish to take into consideration seasonality effects. And then finally, we will talk about a more extensive model, which is called Holt-Winters method for seasonal forecasting, which basically takes into consideration all possible factors that might constitute the demand, such as the linear trend and the seasonality factor. As a matter of fact, seasonality or the seasonal pattern for demand appears in many different types of consumer products. For instance, if you talk about air conditioners, usually they exhibit larger demand during summer. Okay. On the other hand, heaters, for instance, exhibit more demand during cold weather periods. So it's very common to notice seasonality in many different types of consumer products. Here, as shown in the graph below, the seasonal demand pattern appears in the form of a repeating cycle of low and high demand values occurring in a length of time that's less than a year. This is how we define seasonality. So in this graph, for instance, you can see that the demand rises for a specific product until reaching a top value and then goes down and then start rising again until reaching a top value and then it goes down again. This repeating cycle, as mentioned earlier, has a length that's less than a year. So in order to identify our season, as you can see here, the season is actually this length of time, which includes some specific number of periods, and the season could be the whole year, or it could be a quarter, or even less than that. So in order to identify our season, which is constituted of exactly n periods, we can actually look for the lowest demand value, okay, and the next lowest demand value. That's when we can actually identify our repeating cycle, and then we can decide on the value of n, which is again the number of periods in the season. So a common approach for modeling and dealing with seasonality is to use what's called seasonality factor. This seasonality factor has to be estimated based on the historical demand values. So suppose that the recognized season has a length of n periods. The seasonality factor is determined from the given data by comparing the average demand level to the actual demand for each period in the season. So, for each period T, where T is from 1 to N, and again N is the number of periods in a given season, the seasonality factor denoted C sub T is determined. Now, based on this seasonality factor, I can multiply it with an average demand value for the given period, and then from this multiplication, I determine the value of the forecasted demand. We will see how these seasonality factors are used in demand forecasting models. Now, let us see an example of how the seasonality factors can be determined for an application in which the demand is almost level and it exhibits some seasonality changes. So in this example, as you can see, we are talking about the weekly demand for coffee in number of cups. So imagine that we have a coffee vending machine inside the Faculty of Engineering of Cairo University, and we would like, of course, to manage the quantities that should be supplied to these machines. So we would like to have a look at how the demand changes over time. So as you can see here, we have the demand data for 3 weeks. And of course, we have the number of cups of coffee consumed for each day in the week. And of course, we have the total number of consumed coffee cups from that machine. Now, the total number is not really of our concern, but what we are looking for when we calculate the total number is you can see that the demand here is almost level. We have very minor fluctuations happening from week 1 to week 2 to week 3. So now, for each individual demand values each day, you can see that also the values for the demanded coffee, for instance, for Sunday is almost level. The values are very close to each other. Similar thing that you can notice for the other days of the week. As mentioned in the previous lecture, it's very important to plot the data to see how the demand changes over time. Now, as you can see here, we can easily notice that the demand exhibit seasonality very clearly here. Okay, as you can see on Sunday, the demand is low, started to increase, okay, reaches its peak on Tuesday and then goes down again, and then we have a repeating cycle. So now, based on the distribution of the demand over the days that we have, we can see that, of course, our repeating cycle is actually a weekly repeating cycle, which means that when we look for the value of n capital, in this case, it should be 5, because we are talking about 5 days a week, and a repeating cycle actually happens every 5 days. So in order to estimate the value of the seasonality factor based on the given demand information, okay, and since the demand information in our case is actually almost level, so what we are going to do is we are going simply to calculate the average demand per day. The average daily demand for the whole number of demand information that we have. Here we have 15 demand values. We calculate their average. The average in this case is 55.8. Now, if we divide the demand in each day by the value of the average demand, we come up with some values here in the last column of the table. Now, these values are actually the seasonality factors that correspond to the data that we have. Now, By looking at the data or the data in the last column, you can see that, for instance, on Sunday, the demand value, or actually the demand divided by the average demand, which is a representation of the seasonality factor, is 0.86. When you look at the value again on Sunday for the next week, it's 0.79. The value again in the third week is 0.81. So it's like we are talking about an average value here for that ratio, which is again a representation of the seasonality factor. So this means what? This means I can, if I take the average value for these three values, okay, this might give us some estimation of the seasonality factor for the day Sunday. And we can, of course, repeat the same thing for the other days of the week. So when we do that, okay, we obtain the average ratio between the demand, the daily demand, and the average overall demand. And this is the estimation for the seasonality factor for the given data. The seasonality factor has to sum up to a total value of n capital, which is equals 5 in our case here, because we are talking about n capital equals 5, because we are talking about 5 days a week, right? So they have to sum up to a total value that is exactly n. Now, if this is not the case, then we have to do some adjustments to the values assigned to the seasonality factors given here in order to have a total summation that exactly equals 5. In this case, in this specific case, actually the summation was exactly 5. So it's sufficient to use the values as is without any changes. Later on, we'll see some other examples in which we will adjust the values of the seasonality factors. Now, based on the seasonality factors for each day, now if I wish to calculate the forecasted demand for the next week, I can do that by multiplying the average demand value, which is here 5.8, which was calculated earlier for the overall values of the demand, historical demand values, and then multiply this value by the seasonality factor of each day of the week. This will give us the forecasted demand for the next week, and these are the values for each specific day. Of course, as you can see here, the forecasted demand is not actually an integer, even though, of course, we are talking about an application in which the demand is actually represented by the number of cups of coffee. So this means what actually? If you think of the forecasted demand as an average value that you would expect to have to have in the future. So as an average value, doesn't have to be an integer. Of course, you can take this value, round it up or down, and get an integer estimate for the forecast. So in the previous model, we have seen how to come up with an estimate for the seasonality factor of each day of the week, which is, of course, the season that we talked about in our example, and then how to use these seasonality factors to come up with the forecasted demand. And of course, it was for a very simple application in which the demand is almost level. Now we will talk about a different technique in which we actually use moving averages to estimate the values of the seasonality factors, and we will see also how to use them with moving average techniques to predict future demand. This will be demonstrated through a very simple example in which we have the demand information is given for the previous 2 years in this table, And each year is divided into 4 quarters, and of course the demand values are given for each quarter in each year. As usual, we will also always be interested in plotting the demand information with respect to time to see how it changes over time. As you can see here, we have seasonality, very apparent seasonality effect in the historical demand information. And of course, this highlights the necessity of using seasonality factors in developing forecasts for this data. Now, let us see how to use moving averages to estimate the values of the seasonality factors. First, the first step, okay, you have actually to use the moving average technique with the given demand information such that the number of periods considered in the moving average calculations is exactly n capital, which is the number of periods in a season. And of course, in this case, the season is the whole year divided into 4 quarters. So, as we have seen in the previous lecture, the calculation of the moving average value here in this period depends on calculating what the average value of the demand for the previous 4 quarters. And of course, we do the same for the other values here for the other quarters. So this is actually gives us what the moving average based on 4 number of periods. Next, we take these values, put them in what's called the centralized moving average value. So it's like if I have 4 quarters in each year, so the center value is exactly at 2.5. So this, what happens here, we move the centered value to a hypothetical period indexed as 2.5. And again, we move the other historical demand values similarly to hypothetical intermediate centered values for the periods. Next, we will see how to re-centralize these values to put them exactly on a specific index for T. Now, what happens here is, if we take the average value of these two centered moving averages, we will get the value of 39. Now, this value, we are going to put this value in period 3. Again, we take the average of these two values and put the result at the index 4, and so on. So at the end, we come up with these values, which represent what? The centered moving averages at specific indices of the time period. Now, for the remaining time periods in which we do not have centered moving average, which are specifically period 1, 2, 7, and 8, we calculate an estimated moving average by taking the average of these two values and putting it here and here in the first 2 periods. We do the same, okay, with these 2 periods. We calculate that average centered moving average and put it here at period 7 and in period 8. At the end, we come up with this table, which actually represents what? It represents the centered, what's called centered moving average that corresponds to each period given in the historical demand values. Next, we will see how to use this centered moving average in order to estimate the seasonality factors. So here, as you can see, we have a table in which we have the historical demand information given in this column, and we have the centered moving average, which is calculated as shown in the previous slide. And of course, just like what we did for the first example, we divide dt by the centered moving average value at the same period. And this will give us what's called the BC ratio. Okay, so this column includes all the calculated BC ratios for each period. Now, just like what we did again in the first example, we take the values calculated for the BC ratio, which corresponds to 8 periods, and then we take the average. Okay, for instance, the average of period 1 and period 5 BC ratios will give us 0.27. The average for period 2 and period 6 will give us 0.67, and this will become our estimation for the seasonality factor. Again, we have to make sure that the summation of the seasonality factors for the 4 periods equals exactly 4. In our case, it's not exactly 4. So what we are going to do is we are going to adjust these factors in order to have exactly the summation of 4. The adjustment is done in a very simple approach. What we do is you can, for instance, in the first quarter, you take this value 0.27 divided by 4.06 and then multiplied by 4. Okay, this is how we come up with the value 0.26. Of course, when you do these calculations, actually, the values are not exactly 0.26. So it's like you have to do your approximation. Usually, when we do these approximations to facilitate our calculations, we will use 2 digits after the decimal point. Okay. So at the end, these are the adjusted factors which represent the seasonality factors for the 4 periods in our season. Next, using this seasonality factor, we calculate something called decentralized demand. In the decentralized demand, what we do is we divide the historical demand value in a period by the seasonality factor which was estimated for that period of the season. This will give us the value of the decentralized demand. Now, why do we do that? The main idea here is when we calculate the decentralized demand, we are actually neglecting the seasonality effect on the given historical demand values. So the value that we achieve here in the last column is something that represents how the average demand or how the demand would change on average without having any seasonality effect. The decentralized demand is actually the cornerstone of this technique because you can use it by applying any other moving average technique, probably exponential smoothing or any suitable technique to predict future demand that is, in this case, will be decentralized future demand. And then if you have a prediction for a decentralized future demand, you can simply multiply it by the seasonality factor that corresponds to that period, and then you will come up with your forecasted demand for that specific period that takes into consideration the seasonality effect again. So that's exactly what we did here. In this example, based on the decentralized demand values, we are going to apply the moving average method with 6 periods. And here I'm specifically using 6 periods in order to highlight the generality of the models that you can apply to the decentralized demand. So remember, when we used moving average to calculate the seasonality factors in the process that we described earlier, we applied moving average with 4 periods, and actually we had to do that because each season is constituted of 4 quarters or 4 periods. But when you come up with the decentralized demand value, you can apply any forecasting technique, any moving average forecasting technique, or exponential smoothing, for instance, to come up with a forecast for the decentralized demand in the future. So here I decided to use moving average of 6 periods to do that. Now these values are the moving averages based on 6 periods calculations, and then what I'm going to do is I'm going to multiply these moving averages with the corresponding seasonal factors in a period, and this will give us the forecasted demand in that period. So here 41.32, the first value of the moving average based on 6 periods is calculated based on what? Based on the previous historical decentralized demand values in the 6 periods, right? Now this value would represent the forecasted demand for period 7 based on the decentralized demand. So it's like the forecasted decentralized demand for period 7. Now, if I multiply this value by the seasonality factor that corresponds to period 7, I will come up with 71.67. And that's exactly the forecast for period 7 using this technique. Similarly, the forecast for period 8 can be calculated, and then for period 9. And of course, when I do calculate the forecast for period 9, I use the seasonality factor 0.26, which is basically the seasonality factor of the first period in the season. Okay, so this is how we develop our forecasting based on the moving average technique with seasonality factors. Next, we will see another technique which is a bit more complicated than the other two techniques that we have demonstrated earlier, which is called the Holt-Winters model for seasonal forecasting. This technique actually tries to integrate trend with seasonality in a very similar fashion. The trend component is very similar actually to the basic Holt's model that we have described in the previous lecture. But with integrating the seasonality factor, of course, the relationships should include some sort of seasonality effect or seasonality factor calculations and integrated into the trend model that was given by Holt. So here, as you can see here, the model is components are as follows. First, we have an intercept that's updated with this equation. Okay, this is very similar to the calculations that you will find in Holt's model. You have alpha, which is a factor in the model, multiplied by dt, which is the historical demand information in period t, but now it's divided by this seasonal factor, which of course has to be estimated before using it in this equation. And then we have 1 minus alpha multiplied by st minus 1 plus gt minus 1, which is basically the forecast based on period t minus 1. And then the slope is updated using the next equation here. Okay. I think actually if you look at Holt's model, actually you'll see that it's basically the same equation that we have used before. Now, Seasonal factors are also updated in this model. Okay, and this is how how the seasonal factors are updated based on the historical demand values and the intercept value. And here you will notice that we have another parameter, which is gamma, added to the model, okay, which is used again for updating the seasonal factors. And then the forecast is finally calculated using very simple relationship in which you have the intercept plus the slope times delta t, okay, which is the usual Hulse forecast, and then times the seasonality factor. Okay, so these are the main equations of this model. In order to use Holt-Winters model, actually, you have to come up with initial values for the seasonality factors, just like what we did in the previous two models. In order to do that here, okay, we deal with the historical demand information to come up with two estimates at the beginning, V1 and V2, and those actually represent something like the center or the average demand per season for the last two seasons of historical demand information. And then based on V1 and V2, we define the slope and intercept using these equations. These are the initial slope and intercept. As you can see here, this relationship is very simple. The slope is simply the difference between V2 and V1 divided by N capital, which is again the number of periods in a season. So it's like you have the average demand values in both seasons and you divide it by N. That's basically the slope. Here, the value here is again is the initial estimated slope value. Similarly, we have another equation for calculating the initial estimated intercept value. What remains is now we need initial values for what? Initial values for the seasonal factors, okay, and they are calculated using this equation. Now, we are going to see how this is done through an example in the next slides. Now, we will demonstrate how the calculations are done through a simple example. In this example, we use the same data that we had in the previous example. What we will do is actually we will have an additional index here, which is J. This J actually is used to index the historical demand periods, which actually starts at -7 and moves to 0. Okay. Now, the first step, as I mentioned, is to calculate the values of V1 and V2. And here are the formulas for calculating V1 and V2. Okay, they are basically, again, the average demand values for the whole season. So for the first season here, okay, we calculate the average for these four numbers, and for the second season, we calculate the average for these four numbers. The average for the first four numbers is actually V1. The average for the second four numbers is actually V2. That's how we come up with these numbers. Next, we will calculate the initial slope and intercept using very simple formula. Here, G naught equals V2 minus V1 divided by N, which is in our case 1.75. That's the initial slope. The initial intercept is node equals V2 plus G0, G naught, multiplied by N minus 1 divided by 2, which is in our case 48.375. Next, we calculate the initial seasonal factors, which are estimated using the following relationship. As you can see here, we have C sub J, which is actually the estimated seasonal factor for period J equals D sub T, which is the historical demand value at the period T, which corresponds to, of course, index J. And then in the denominator, we have here V sub I, which actually equals one of the calculated values here, V1 or V2, depending on which season we are talking, plus N plus 1 divided by 2 minus K times G naught. Now we have, as you noticed here, an additional index K used in addition to, of course, the index I. Index I equals 1 for the first season and equals 2 for the second season. Now, what about index K? Index K is actually the quarter index within a season. So, for instance, the first quarter will have K equals 1, okay, and that is in this case, applicable to J equals negative 2n plus 1, and of course the value of J equals negative n plus 1. That means what? This is the first period either in or the first quarter either in the first season or in the second season. When K equals 2, then we talk about the second quarter in the season, either in the first season or the second season. This is what index K means. Now, based on this formula, these are the calculated CG values in the last column of this table. Again, these CG values are actually the seasonality factors that correspond to each period in the historical demand information. So you should expect what we are going to do next. Of course, we are going to take the average value for each quarter. Okay, so it's like we will take these two values, for instance. Okay, take the average value of both to calculate the average seasonal factor for the first quarter in a season. And we'll do the same for the other quarters as well. So these are the values that we have calculated as the average seasonality factors for the 4 quarters in a season. The summation here equals 4.1. As we have learned before, we have to adjust these factors so that the summation should be exactly 4, which is the number of quarters or the number of periods in a season. So after adjusting these values, okay, we come up with, again, these values. And again, remember, okay, it's for manual calculations, it's totally sufficient to just have an approximation of the seasonal factors as using 2 digits after the decimal point. Now, we have estimated the initial values that are necessary to develop our forecasts, initial values that include the initial slope, the initial intercept, and the initial seasonality factors for each quarter. Next, we are going to use the Holt-Winters formulas to develop our forecasts for future demand. The calculation here is very simple, straightforward. If you are using alpha of 0.15, beta of 0.2, gamma of 0.08, then the calculation is straightforward. In the initial period, okay, the initial forecast or the initial values for the slope and the intercept are available here. Okay, you just apply the formulas to come up with the updates for G1, S1, and then, of course, again, the starting value for CT is given here based on the calculated, of course, seasonal factors, and then you apply the formula to calculate the value of the forecasted demand. The value of the forecasted demand here represents what the forecasted demand for the for actually the first period in the given data. So this number is actually the forecasted demand for what? Forecasted demand for the first period. How did we come up with this number? Well, it's basically simply the summation of this number, which is 1.75 plus 48.375 times 0.24. This will give you 12.04. Okay, so this is the forecast based on the initial values for the slope and intercept, and of course the seasonality factor. Next, okay, to calculate the forecast here, what you need is you have to sum up this value, okay, which is of course updated using the formula given in the previous slide, and then of course this another value which is updated as well. Okay, sum up these two values and then multiply them by the corresponding seasonal factor. This will give you the forecasted value here, and so on. You can repeat this for any future period. Well, that's it for today's lecture. In addition to these slides, actually, I will have also a link for a YouTube video in which you will find explanation of how to use Microsoft Excel to conduct the Holt Winters calculations. Thank you for your attention and see you next week.